In this video, we're going to describe force fields or non-contact forces by drawing a map of vectors to represent the direction and magnitude of the force in different locations. So let's start by defining what a force field is. A force field is a vector field that corresponds with a non-contact force acting on a particle in various positions in space. So whether you're talking about gravity or electrostatic force or magnetic force, a vector field is basically arrows representing the direction and magnitude of the force that would be acting on a test object in that particular location in space. You will see these arrows basically making a picture that is a map of which direction and magnitude the force would go in that spot. So let's start with gravity because gravity is the simplest. Gravity only has one type of force. It's attracting force. There is no such thing as a repulsive gravity. If you were to look around the Earth has mass, which means the Earth is going to experience the force of gravity. It is also going to impart a force of gravity on any object that has mass that is around the Earth's general vicinity. So if you imagine placing yourself around the Earth, a vector field is going to be an arrow that represents the direction and magnitude that the force of gravity would be pulling on you, somebody with mass, around the Earth. Our field is going to look very simple. It's basically just a bunch of vectors pointing towards the Earth. Now, we'll see other representations of this, but this is the general idea. The force is always inward towards the Earth, showing that attractive force. Now, Einstein famously thought of gravity not as these vectors, but rather gravity as the distortion of space-time fabric. So if you imagine space-time being this two-dimensional fabric, so again, simplification because our brains have a hard time understanding a three-dimensional, and we place the Earth or any object that has mass in this space-time fabric, it is going to distort that space-time. Think of this well where it's distorting space-time and bending it inward toward itself. If you were a test mass, think like a marble in this fabric, and you were to place that test mass somewhere on here, the gravity is the direction that that test mass would start to move. If you're fairly close to the Earth, that gravity is going to pull you more dramatically than if you're farther away from the Earth. As we've seen through the universal law of gravitation, distance has an impact on the force of gravity. The farther you are away, the less gravity tugs. Now, we can think of this more generally as the distortion being impacted by how much mass the object that we are looking at actually has. The more mass of the object, the more space-time bends or curves, and then the less mass of the object, the less it will bend or curve, which means it's going to impact the things around it a little bit less. Now, the reality is the universe is filled with things that have mass, so there is not just one space-time bend. Everything with mass is bending space-time a little bit. So if you are flying through space, you're going to be impacted by all of the different things that are acting. And space-time is not smooth and flat. Now, we have a hard time drawing that kind of picture, so we will typically draw the gravity field as a bunch of vectors, a bunch of arrows. So to represent the strength of the field here, rather than seeing it as the bending of space-time, we are instead going to draw it as either a larger vector. So the more magnitude of the vector will represent a stronger force. So the closer you are to the Earth, the longer the vector becomes. Or you might see a field that's represented like this, where it's just single vector lines. And when this is the case, the closer the vectors are together, the vector density, we are going to indicate a stronger field there. The farther away you get from the Earth, the more the vectors are spread out, and the less strong the force is going to be. Now, when we shift to electric fields, the biggest change here is electric fields could be repulsive or attractive. So we need to indicate a direction here. It's not always going to be pointing inward. Um, our standard for defining electric fields is it's always going to point in the direction that a positive charge would travel. We call this a test charge. So you would imagine that you'd place a positive proton somewhere around an object, and then the vector is going to represent the direction that that positive test charge would move around that object. So if I place my positive test charge here next to another positive charge, positive and positive like charges repel, so we would indicate a vector pushing away. If I was over here, that positive charge would push away in the other direction. Notice the closer I am, the longer the vector is because the stronger the force. If I kept this up, I would end up seeing forces emanating in all directions off of this positive charge. If I did the same thing around a negatively charged object, this positive test charge would be attracted, positive and negative attract, and the same thing would be the case anywhere you go. So around a negative object, those positive charges are being attracted. So one of the ways I think of it is a positive is like exuding positivity in all directions, and a negative object is pulling that force field inward on itself. So, when you have more than one charge, they will interact in interesting ways. That here we can see two different charges, and it has these emanating kind of curves of a line. We'll see that again in magnetic fields, but we can indicate which one is positive and negative by thinking of our rule. The arrows are representing the direction that a positive charge would travel. So if I place a positive charge anywhere on one of these lines, it's going to travel in that direction, which means it's moving away from this one on the left, moving toward the one on the right, moving away if it's a positive charge, the left must be positive, moving toward, if it's a positive charge, the right must be negative. Which means if I were to place something in one of these curves, it actually won't go directly at the negative, it will move sideways because the positive and the negative are both impacting it a little bit. We can also predict what field lines might look like if you have two positive charges. It's pretty easy to think about on the sides. If I place a positive charge over here on the left, it's obviously going to be repelled by both of these, and it's going to move off to the left. If you do the same thing on the right, if you repelled by both of these, move to the right. If I place one kind of in the middle here above, it's going to be repelled by both of these pretty equally, and it'll actually send it upward. So in the resulting lines on this, it's actually going to look something like this. So that there's kind of this middle ground area that will push up and out or down and out. Um, Officially, there's somewhere in the middle that's like perfectly on that razor's edge, but we don't really draw that. We just show these arrows that are arcing away. All right. A more challenging way to think about this. Here is a common question that you need to be familiar with. Two isolated point charges, one that is -7 microcoulombs here at position B, and +2 microcoulombs are at a fixed distance apart. At which point, A, B, C, or D, is it possible for the electric field strength to be zero? So we are imagining here there is a position that it is possible that if you place a positive test charge, you would be attracted to one of these in the exact same amount as it is repelled by the other one, and things will cancel out. So it is helpful, I think, to try to imagine what each electric field would look like independently. So let's start with B here. This is a negative charge. Negative is going to have an electric field that is pulling inward on it. The closer you are, the larger the vector size. So the farther out we go, that vector gets smaller. So I'm representing in pink arrows here the vectors coming inward on that negative charge. If I think of this blue one, it's +2, which means it won't have as much force because it's a little bit smaller of a charge. This one's positive, so it's going to emanate outward. And if I draw in those vectors, the farther away you get, the smaller they become. Now, if I'm looking at all of these things at A, B, C, and D, if I were to add up the vectors that are in those spots, at A, I see there's a pink vector to the right, and then I don't even have drawn a blue vector to the left. It would be very, very tiny if it was there. We would see that pink is definitely larger than blue. They're opposite directions, but they're not going to perfectly cancel. At B, B is being really nothing for the pink because it's right there. It would be a very strong force, and then blue is there, so those don't cancel. Same thing with C. But at D, you'll notice that the vector to the left is about the same as the vector to the right. One way to think about this is you are closer to the smaller charge, and the closeness to the smaller charge ends up canceling out so that it gives you about the same impact as being farther away from the larger charge. So that is something that you'll see later on, but both the distance and the charge impact how big the force field is. At D, we have the possibility that they can cancel each other out. All right, last type of force. Let's look at magnets. Magnets have their own way that we're going to describe the direction. You may remember as a kid that magnets have a north and a south pole. A south and a north pole will attract each other, but two south poles will repel, two north poles will repel. So very similar to positive and negative charges, only this time Every magnet is going to have these two different poles, and we're looking at the orientation of the magnet. The way that we draw a magnetic field around a magnet, our convention is the field lines will always point from the North Pole to the South Pole. Now, if we have a single bar magnet like this, a compass would align to these field lines, and basically lines will come out of the north, curve around, and go back into the south. So this is very similar to when we saw the positive and negative charges, only now it's built into the same magnet. We will see other orientations of these magnets later on. A horseshoe magnet or two different magnets, but the lines will always go from north to south. Here is a horseshoe magnet. It's basically just bar magnet that's been bent in half. So we don't see quite the large arcs. Instead, it's much more concentrated that the north and goes to the south. This strengthens the magnetic field because these are closer together in distance, like we saw with electricity and gravity, impacts the force of the field. Now, the Earth is actually a magnet. You might experience this if you ever use a compass. And a compass, you might remember if you use it, points to the North Pole. Turns out that it is the North Pole of the compass that is pointing up towards the North Pole. That is because the Earth is a giant magnet. It's flipped from the way that you would expect. The magnetic South Pole is up in the geographic North Pole, which is why our compasses point to the north. The north is attracted to the south. Um, and that magnetic north is what we call it, even though it's a south pole of a magnet. The magnetic north is not necessarily at the geographic North Pole. It is shifting over time, which is something that is kind of a mystery. We've seen in the past that this magnetic field has flipped in Earth's history, and we're not totally sure why. It has something to do with the outer core, but you should know that the Earth is a magnet, which is why compasses align to that magnetic field that is being represented there. So, in this lesson, you should be able to draw gravitational fields using vectors, always attracting. You should also draw gravitational fields, imagining it as a warping of space-time and understanding that Einsteinian model. You should be able to draw electric fields as point charges and charged plates. We will see those later on. And then be able to draw magnetic fields around a north and a south